So what this talks about basically is not only exploiting the heap in double freeze, but doing it in a way that is, we don't traditionally think of the heap that way. We normally think of the heap in a manner that's very linear and very buffer overflow style, buffer overflow-esque. So what I'm hoping to do is get everybody thinking a little bit differently and kind of think about the fringe cases a little bit more, because like it or not, that's kind of the way the world's going. I've got a lot of slides. I had to cut a little bit out of the slides, out of the content, so I apologize to you, and I'm going to have to talk fast. Real basically, the heap, it's just a globally scoped data structure. It's persistent. It's for dynamically allocated memory that exists until you free it. It kind of works like the stack. It's similar in that scope, except for the fact that it's not local to a function. As I said, it exists until free. The glibc implementation was originally written by Doug Lee. That's the one that most everyone's familiar with. It's been revamped by Wolfram Glogger, and it's called ptmalloc 2. It's a slight variant. There's not a lot of huge differences there. The biggest two being multiple heaps and arenas are supported, and the support for threads. What I worked on with this was glibc 2.4. That was what's current at the time. I looked last night, and glibc 2.6 was the current, and I pulled it down and took a look at it, and everything was pretty much the same. So not a whole lot had changed there. As I said, the multiple heaps are supported, so the heap's a little bit of a misnomer. Something that the Unix world isn't so much used to, but something that's fairly common in the Windows world. Heaps normally allocated either traditionally via sbreak, which extends the data segment, but glibc, if it has mmap, then it will actually prefer to use that and let the operating system deal with how it's done. Allocation requests are filled either from the top chunk or from free lists, and I'm going to get into those a little bit in 4 or 5 slides or so. Allocated chunks are navigated by its size, whereas free chunks are navigated by the linked list, and adjacent free blocks will be coalesced into a single one, so that implies that no 2 free blocks will ever be adjacent to each other. As far as the data structures, every heap starts off with a heap info structure, followed by a malloc state structure. The heap info structure isn't used a whole lot. In fact, I think off the top of my head that it's only referenced once throughout the entire glibc code. Most everything that deals with navigating the heap is done through the malloc state structure, which is what defines the arena. And then, of course, any number of malloc chunk structures, which are the ones that pretty much everyone's familiar with. Heap info structure it defines the size of the heap, pointer to the arena, and pointer to the previous heap if one exists. The malloc state structure is a little bit more interesting. It has the mutual exclusions that allow for multi-threaded and async safe or async mostly safe code using malloc. Flags indicating the status, whether the heap is contiguous or not, so on and so forth. And then, of course, arrays of pointers to malloc chunks, which are fast-binned in normal size chunks, and then pointers to the next malloc state structure. The malloc state structure, or the malloc chunk, contains the size of the previous adjacent chunk, size of the current chunk, and then if free, there's a pointer to the next free block in the previous free block. Pretty much everyone's probably going to be familiar with that in here. There's the structure of it. It's probably the most well-known data structure in the heap. It's semi-universal. Pretty important point, especially when dealing with double freeze, is that malloc chunks have 2 different representations, even though they contain the same physical data structure. An allocated block of memory kind of goes like this. It's the size of the previous chunk, size of the current chunk. Then we've got 3 flags. A lot of the documentation, even the documentation in the source code is currently wrong. There's 3 flags there for previous in use, whether the chunk is mem-mapped, and then if it's in a non-main arena. Free chunks, same physical structure, except where there used to be just a pointer to user data, there's now the two pointers to the previous and the prior chunk in the linked list, and of course the ISMA mmapped flag is gone. Chunks that are mmapped just get mem unmapped, so there's no reason for them to ever be in a free list. Free blocks get stuck into bins, which is basically the same thing as a free list. It's just the glibc term for it. There's two different types of free list, fast bins and normal bins. The fast bins are basically some of the checks are skipped on them. They're not coalesced. They're not sorted. Whereas the normal size chunks, depending on what size, they have two different sizes of normal size chunks. One that's the smaller ones and the larger ones, and they're sorted a little bit differently. Normal size bins split into three basic categories. The first bin is the unsorted bin. It's been talked about in a couple different papers as far as buffer overflows and things and exploiting that. The small normal bin chunks are the small normal chunk bins, and the large ones. Larger requests get serviced via mmap, and like I said, there's really no bin form, there's no purpose. It gets just m unmapped. Fast bins, they're removed in a LIFO manner. That actually gives us a lot of control. Blocks that we free, we can immediately get right back if necessary. The range from 0 to 80 bytes, anything larger than that falls into a normal size bin, with the default size, the default max size being 64 bytes. And then there's a table there with the what chunk sizes get stored in there and into the various bins. Normal bins, as I said, contain the same physical structure as a fast bin. Blocks of less than 512 bytes fall into the small bin range. They're also not sorted, and it's actually possible for fast bin chunks to get coalesced at a certain point when allocating other memories, and under certain conditions, malloc consolidate will get called in and actually consolidate fast bins. So there's a little bit of overlap there, but it makes sense when you actually look at it and think about it for a minute. Chunks larger than 512 bytes and less than 128K fall into the normal size bin. They get sorted in the smallest descending order, and they get pulled out in FIFO order, which isn't really conducive to what we'd like. So the fast bins and the small normal size bins are kind of better targets because we yield better control over them. In addition to that, we have two special chunks. We have the top chunk and the last remainder chunk. Neither one of those are ever in any bin. The top chunk borders the end of memory. It's used for allocation if possible. If there's nothing, like if a request comes in and you can't fill it out of one of the free lists, then it tries to take it out of the top chunk. If that fails, then it'll try to extend the top chunk. And if that fails, then it'll try to create a new arena and create a new heap. When a chunk that's getting freed borders the top chunk, it gets folded back into it, and it becomes the top chunk essentially. Inside of the code base, it's treated like it always exists, and therefore it's treated a little bit special, and it can grow and shrink as well, obviously. The last remainder is the result of allocation requests that's smaller than any of the size chunks. When it gets split, and what's left of that gets pointed to by the last remainder chunk, or becomes the last remainder chunk. Just a quick few notes on heap operations. When you create a heap, it's created implicitly. It's not like Windows. You can't call heap create or anything like that. And when you, not even sure what I was trying to say there. When you allocate a block, fast blocks or fast bin blocks can't cause consolidation small normal size ones can cause it under certain circumstances, and large normal ones always call that, which is something we're going to exploit and use to our advantage a little bit later. When resizing a chunk, one of the most important things for us to be aware of is that it can actually cause our chunk to be freed, which may or may not be what we want depending on the situation. And then when freeing chunks, it can also cause trigger consolidation, and can actually cause the heap to be resized, which in turn can cause problems for us. Moving into the subject matter, what we're looking at is double freeze. They're an instance of dangling pointers you use after free. They've been known about for a while. There's nothing really extraordinary about them other than they're kind of providing interesting insight into the way that the heap works. In the example there, basically we have two calls to free with the same pointer, and it's obviously invalid. And double freeze have surprisingly not really been talked about a whole lot. When I looked at the Voodoo Malloc tricks and Once Upon a Free papers, which were the kind of the original heap exploitation papers, there was nothing in there. Advanced Dougley's Malloc exploits mentions them, but it's it's in passing. The Malloc Maleficarium mentions it, but they actually it's in a glibc string, so they don't even actually mention it. It's just from a copy of some code that they put in there. The Shellcoder's Handbook has a single paragraph far down into the book. It tells you a little bit about them, that they're not really exploitable, that most systems have protections against them. It doesn't happen a whole lot, but if you do see that they're not setting the pointer to null after freeing it, that you should probably look for them. However, the Art of Software Security Assessment, which just came out not too long ago, did talk about it a little bit. And they, in the single sentence there, kind of summarized the problem in saying that if memory is reused between successive calls to freeze, the memory block could be entered into the free list twice, which is kind of the crux of the problem in most instances. In traditional double free exploitation, there's only been one talk that I could really find, and it was a post to a mailing list that dealt with an exploit for the CVS server bug that came out in 2003. It was actually it was the only thing that I can find that actually talked about exploiting them, whereas everything else either just mentioned them in passing or just didn't mention them at all. The biggest thing to remember here, though, is that two different chunks can exist, or the same chunk can exist in two different places and contain two different states at the same time. As you can see there's the representation of the two of them again, just for your memory. What happens when you free a chunk the first time is that your chunk ends up in the free list, which gets linked in. You have a forward and a backwards pointer. The gray chunk is our chunk, obviously. Now, if you think about it, if you called free again, it's kind of curious what could happen. You'd end up with it in the list twice. So if you got it allocated back, it would still be in the free list. It would exist in both places at the same time, which is what I tried to depict in this image, but it was kind of hard to do in a manner that could actually be shown halfway decently. Basically, the problem is that when it gets allocated, the pointer that you're looking at, or the pointer that gets returned to you by malloc, points in the metadata on the instance that's in the heap or in the free list still. Traditional exploitation of it used the unlink macro, just like pretty much everything out there dealing with the heap. It was created by Solar Designer, or found by Solar Designer in a JPEG bug in Netscape. Back then, that's basically what it looked like. We just took the two pointers and dereferenced the pointer to the pointer, and overwrote an arbitrary memory address with 5 or 4 bytes of our choice, or size of a pointer of our choice. So in the process of doing a traditional exploitation, you just had to get the same block freed twice, get one block allocated back to you, overwrite the forward and the back pointers, or maybe even one of them, depending on the instance. Allocate the second instance of the block on the free list, and so when it actually gets unlinked, you would perform that overwrite. It's actually kind of the same thing as traditional buffer overflow, except instead of trying to call free after you've overflown, you're calling malloc to get it back. It's pretty good. It worked, but like all things, it kind of ended. It's been hardened pretty much everywhere, and then on top of it, double freeze protections have been implemented in a lot of different places. The new unlinked macro specifically checks the sanity of the lists to make sure that what they point to is what's actually being freed. And this is by and large the result of people actively exploiting it. In a specific example, what we're talking about is a couple of multiple free conditions that were found in Modoth Kerberos versions 5.2, 5.3. Pretty much everyone that I looked at, but I didn't go digging too deep. The bug itself probably isn't that big of a deal. Getting a reliable exploit off of it has been non-trivial. And on top of that, the section of code it only gets compiled conditionally. So not everybody is going to be even using this piece of code. In fact, a lot of people are not going to be using it. Interestingly enough, it looks like it came from an old version of ASN1 compiler out of Heimdall. Newer versions don't have the same problem, but they have a lot of other problems. The code that gets generated from your .asn1 files, if you're using it, you should really take a look at that code because it's got a lot of problems. And it's kind of one of those things that you have to expect to have problems. It's program reading code and generating code off of that. Initially I had a lot of code in here, and it was kind of hard to represent in slides, so I opted for diagrams instead. I apologize to everybody that would prefer to see code. I would have preferred to see code, but it just wasn't working. So in the first vulnerability, what we have is that the function decode neg token init calls down into decode mech type list, which in turn calls decode mech type. And if any of these functions error out, then they call their free function, which for decode neg token init is the free neg token init, and for free mech type list it's for decode mech type list it's free mech type list, which in turn free mech type list is also called by free neg token init, and they both call free data to val. The second one's a little bit more complicated. It's the same code path: decode mech type list, decode mech type, decode OID, and dir get OID. And in turn, the problem occurs again that essentially they have wrapped or nested error handling functions that all propagate the error back up, and they all free the same memory. In this instance, it's the component structure, the components element of a structure, and this one's actually directly user controlled. Earlier versions of glibc had no thread safety. They're still listed as being not async safe. And looking at it and trying to deliver signals, I found that you couldn't really do a whole lot with it. So whether it's asynchronous or not is quite possibly debatable. But the lack of thread safety was originally demonstrated in delivering signals for fun and profit, which was a pretty good paper that a lot of people don't seem to be aware of, and they haven't actually. It's fairly underappreciated. Thread safety is a key difference between Dudley's malloc and PT malloc, and it's provided by two mutual exclusions in the code base. One is by the list lock mutex, which is locked mostly when causing or creating a new heap or arena, and the reason it's used is just because the per arena mutex may not have been acquired, and that may be why we're creating the new heap in the first place. In that it effectively blocks two threads from entering the same code or entering critical sections at the same time, and does fairly good job of that, obviously. However, the code base itself is written in a manner that's it's only meant to be executed in a linear fashion. And, the mutexes are good, they work, they keep you from getting in there at the same time, but it doesn't stop someone from creatively creatively using threads, or using the threads to creatively take the sequence of events out of order. A lot of those assumptions, as far as the linear execution of the program, are actually found in the double free protections. However, I don't really fault the glibc developers if you can't really say, no matter how many protections they put in there, if you have a buffer overflow in your code, they can only do so much to protect you from messing yourself up. Same thing applies to double frees. The double free protections and normal size chunks. The first check that it does is it checks to make sure that the chunk being currently freed is not the top chunk for the arena. Not really a problem. Most of the time, what you'll most likely encounter is that there's already been other chunks that have been allocated, so you're not next to free in the first place. Where I did run into issues with this is where I had a test program that only had my allocations, and then I kind of ran into problems. I don't think I've ever tripped this one though, so it really wasn't even something I had to deal with a whole lot. The next check first checks that the arena is contiguous, and then it checks to make sure that the next chunk is not outside the bounds of the arena. One obvious way to bypass that is to make the chunk the arena non-contiguous. I found that it was actually kind of hard to just create that or to cause that condition. You could do it, but when I did tests on it, I think it took something like 100 threads allocating large amounts of memory and not freeing it to actually create a new arena. But when it did happen, every single time that I tested it, it actually resulted in a non-contiguous heap. Nonetheless, doing that it messes with the state of the heap, and it makes it more complex. We're already kind of dealing with a complex issue in a very small time frame, so the more complexity we can take out of it, the better off we're actually going to be. And again, I never even ran into that instance. It's going to be something more along the lines for buffer overflow that check actually is going to occur. The last check in the normal size freeze, however, or the normal size chunks, there's really no way around it in a linear sense. And all the other ones, you could manipulate the layout of the heap to be able to bypass them. However, this one checks to make sure that the next chunk actually lists that the chunk prior, or the chunk currently being freed, is currently in use. However, this is where threads come into play, because of the fact that you can have two threads and have this data structure shared between them. You can actually cause a free, then cause a free in one thread, allocation in the other thread of the same size. Exploit the fact that you get the LIFO, exploit the LIFO manner of it and get the same chunk back, and then have the other double free occur. When that happens, you actually bypass all of these checks, because to libc, it's not actually a double free. The chunk is actually allocated. However, when the chunk that allocated it back goes to do something with it, it's going to invalid reference to the heap. So it's kind of a buffer overflow, but without the buffer. Fast bin chunks are much better. They sacrifice a lot of things in the name of speed, and unfortunately one of them is the security of the double free protections. The only relevant check is that the bin index for that chunk is not equal to the current chunk. And what happens when you free it and it gets put onto the list, it ends up as being the top chunk in the index. So this check right there just checks to make sure that the chunk being freed right now is not the same chunk that was freed most recently. In this, we have a reliable method for causing a multiple free condition. If we can get another chunk in the same bin freed prior to that second or multiple free, then this check is easily bypassed. So, taking what we know and applying it, if we want to exploit a normal size chunk, we can't get colorless with the top chunk. If the chunk plus its size cannot be outside the bounds of the heap, or the heap needs to be non-contiguous. And then in the next chunk, the previous in use bit must be set. Fast bin chunks, like I said, it's very trivial to bypass. All you need is free pointer 0, free pointer 1, free pointer 0, and you get past it. I apologize for that. Well, you can't see it very well, but in the control flow of this, or the entire function, or the entire control flow down to the vulnerability, is that we enter in through a function called authenticate user GSS, which calls some internal Apache API calls to get the length of the base64 string, allocate memory based off of it, then decode it, and in turn calls GSS accept sec context SP nego, which then in turn calls the decode neg token init and all the way down the chain. So in the first method for exploiting these vulnerabilities, using the second vulnerability and doing it with fast bins. Under this specific instance, and again this is where the code probably would have helped you understand a little bit more, it wasn't exploitable. What you get to write with is an unsigned integer, and because it's what is decoding at that point in time, the first 8 bytes, the first one gets divided by 40, and then the second one gets modded by 40. So you have a very limited subset of what you can actually write, and as a result of that, the pointers, there's just nothing you can do with it unless you can get an address at 40 or something. However, it doesn't invalidate the techniques. It just invalidates them in this specific instance. You're not taking control directly via the linked list operations. You are taking advantage of it, but you're not doing anything like exploiting the unlink macro or similar. What we're actually going to do is cause consolidation to happen and use consolidation to take control. So what we need to have occur is that we need to get 2 chunks of the same size that are within the fast bin chunk range freed. And we need to get them freed interchangeably. So free A, free B, free A, free B. And we can go on that indefinitely unless we cause, in doing so, we screw with another part of the heap. Then we need to get the first chunk allocated back right to it. Then allocate a chunk of memory larger than 512 bytes to cause consolidation. The malloc consolidate code, it first goes through and defines the next chunk. However, because we control the pointer, the next chunk is actually, what we can do is point it to ourselves. When it goes through and does a loop, and it says pointer to next, basically. And so we can basically fake a chunk in there and cause it to process our chunk and kind of shift it down into ours. So we don't get it on the first time through the loop, but we'll get it through the second time. In order to bypass the coalescing of previous and next chunks, and we have to have bit 0 or the low order bit turned on. Mark that the previous is in use. Otherwise, we hit the unlink macro, and depending on the specific state, we potentially won't survive that. We may cause the same thing as what you get if you try to write a buffer overflow using the unlink techniques. And additionally, the next chunk also has to have its previous in use bit set on. Not really a problem, actually. You'd think it'd be a little bit more difficult than it is in that, at least in that initial transition. What we actually do, though, is we abuse the clear and use bit at offset, which takes 2 arguments, the pointer and then an offset, and it actually turns off the least significant bit. So what we can accomplish there is turning off a bit at any particular address that we'd like. So yeah, you've got off by ones, and now we're talking about flipping individual bits. In that, it's useful, but it's hard to hit in any place because of the fact that you have to have those two low order bits to avoid consolidation. So you either have to go through and find a place where that instance is true in both instances, or that those conditions are true in both instances, and what you want to write is actually useful, or you have to have some limited control over what data is before and after. The stack being the most obvious place where you can potentially do that. The next technique is similar, but instead of using the clear bit and clear and use bit at offset, we're using the set head macro, which it essentially just takes the size, takes a pointer and the size, and then ORs it with the previous in use, which in turn means that we can take a pointer plus 4 bytes if you're assuming a 32-bit integer, and turn on the least significant bit there. And you can do that with any particular byte. If you can actually get yield, if you can actually get enough control in the stack to fake chunks in there, you can cause multiple writes to occur. However, again, you have to have those two conditions where you have to have the low order bits turned on both prior and after. This was actually, again, like I said, if we like off by ones, then you can actually do a lot with flipping on one bit. It was an interesting one to play with. I think I duplicated this slide. I apologize. The next instance is that we can actually, if there's a check in the consolidation code that checks to see if the next chunk is equal to the top chunk, and if it is, then it folds it in and assigns the top pointer to the pointer of your what you control, or your pointer. If we can control an integer on the stack, or even have limited control over it, then what's actually possible is that we can take, regardless of where our pointer is, we can actually make it add up to what you do is you do 0xFFFFF minus address that you're wanting to write to, or you're wanting to set the top chunk to, plus address of the top chunk. And that yields, and so that when it actually calculates the address of the next chunk, it looks like you're right next to it. Which in turn, what happens when the top chunk ends up being pointed to wherever you'd like it to be, then whenever allocations occur that aren't filled out of the free list, it occurs, you get pointers back to wherever you just pointed, or wherever you set the top chunk to. So if you were to point it to the stack, for instance, instead of having a chunk of memory that gets returned by malloc or realloc that points to the heap, you get it pointing to the stack, which in turn is going to cause any number of problems depending on where you point it at. The biggest issue there is that you have to have that integer, and you have to know what the address of the top chunk is. Getting back to the multi-threaded stuff, what we have is actually the section of the code at point 0 there. You see that the chunk gets allocated, and in the ... there, it actually processes and performs the writes, and if it increments the pointer as it goes through. And if the last element is over 128, then it calls free OID, which in turn causes which calls free itself, and then free mech type calls free OID, which in turn calls free. So what we're attempting to accomplish here is to get one thread in between point 1 and point 2 prior to the allocation actually occurring at point 0. And the slide basically says what I did. But if we accomplish this, then basically what happens is that the first thread frees the chunk, then the second thread allocates that chunk back to itself, and then the first thread causes the double free. This allows us to bypass the normal bin double free checks. Now, the biggest problem that occurs here is if both threads start at exactly the same time, then how are we going to get them at different places at the same time? And that's not really even dealing with any real-world issues such as network latency or delays or other clients that are connected to the server. So for the sake of purposes here, we're just going to consider a lab to kind of give you an idea of how to accomplish this. The first idea I had when I looked at this was try to use the mutexes against each other to allow them to sync themselves up, basically. The biggest problem that we have there is that malloc doesn't actually call pthread lock, it calls pthread try-lock, or pthread mutex try-lock. And if that fails enough times, then it's actually possible for a new heap to be created, which is absolutely the last thing we want. Second idea that I had was inside of malloc, when it fails to acquire the lock, that is actually it calls pthread mutex lock on the list lock. And so the idea was to get 3 threads in there, 2 of which racing for that lock, and 1 blocking the other one, while I get the first free to occur. That wasn't really considered, basically because, as I said earlier, we're trying to reduce the complexity, and the more threads that we stick in there, the bigger the race that we're trying to win is, and we're already talking about a very small slice of time. The first thing I looked at is, is this a valid concern that I have? Do I really need to worry about this? And indeed, I did. So I tried to find a shorter path through the code, and this isn't. I took real-time or took timestamps from the processor to get an idea of just how long single iterations through loops and how long it was between point A and point B. It's definitely not something that. It's definitely not the most accurate and not the most consistent. As you see when I start talking about the different amount of ticks that it takes an operation to occur, it varies wildly. But it did give me a general idea of how long a particular operation took place on average. So when I looked at it, and I wanted to see how long it took to get from point 1 or point 0 to point 1, I ran using minimal data so that I minimized the amount of times through the loop. I think I used 1 byte. Ran the test 10,001 times. The highest amount of clock ticks that it took was 379,000, whereas the lowest was around 5,600. Which gives you an idea of just how long and how much variance there actually is in the amount of time that it takes for any particular set of operations to occur. However, the average was about 13,000. I went ahead and rounded it to 13,200. So the goal here is to try to save somewhere around 13,200 ticks in hopes of shortening the execution path for one of the threads. When I went through, there was multiple places that there were loops. Unfortunately, there weren't as many as I had hoped. The code was by and large, or in many places, was done in constant time. The big ones being the base64 decode length, and the actual decode of the data, and then the function dir get OID. By looking at those functions, I was able to find a shorter code path that actually resulted in the same size chunk being allocated. An APR base64 decode length. It's a simple while loop that iterates through a pointer to user data that looks it up in a character array of 256 cars to verify that it's actually valid base64, and it keeps walking through until it hits the end of the string or the data is no longer valid base64. Again, when counting the ticks for just a single byte, trying to determine how long it took, It took between 260 and 305 ticks depending on the characters used, and that's because of the actual placement in the array. The high was around 688,000 to 245,000 depending on which character was used, with the average being between 602 and 573. After I ran all of the tests, the average was about 600 ticks per byte saved. So if we can cut up to 8 characters, this is approximately 4,800 ticks saved. And if we cut that out, we also have to consider the base64 decode function, which is also going to get a shorter execution path due to having less data. Ran again 10,001 tests. High tick count of 4,000 with a low of about 1,000, average being about 1,100. Went ahead and rounded it up to 1,150 and multiplied by 8 for each of the 8 bytes that we can emit before we actually get a different size chunk. Multiplied that by the 4,800 ticks that the decode length function saved us, and it actually yielded 14,000 ticks, which is higher than what we were trying to save. In addition to that, we actually needed to consider dir get OID, unless we cause an error earlier on. However, that's not going to suit our purposes because we actually need to hit that free to cause the chain of events to occur. There's 2 different code paths in the loop depending on if the byte being processed is greater than 128 or 80 hex. If it is, then it actually enters a do while loop inside of the other loop. So I had to test both. If an individual byte was less than hex 80, then the high was of 4,000 ticks with a low of 5 ticks. Again, re-emphasizing just how much this can actually vary. With an average of about 150. It took a bit longer when the byte was over 80 or hex 80, with an average of about 388 ticks. So taking all of those averages, trying to save 1,200 ticks, we can cut 6 characters out from the first thread and alternate between being greater than hex 80 and less than 80, so that we have 80, 81, 80, 81, and we can save about approximately 12,840 clock ticks. Or we have the option of cutting 7 characters, putting them all below hex 80, and saving about 1,303. In that, it actually, in lab conditions, it was able to replicate that and get an exploit working. Like I said, it was not reliable and it's hardly trivial. So how realistic is it? It depends on a lot of conditions. I wouldn't want to try to use it in or rely on it in a real life based situation, but it can definitely help you identify shorter code paths even if you can't necessarily use the tick counts out of it. And like I said, it helps you find a decent metric for that. Especially useful on SMP and multi-core machines where things can run concurrently as opposed to having to use the schedule and stuff. An interesting thing about this technique, however, is that when dealing with Linux threads and Linux capabilities, Linux threads didn't properly implement POSIX threads. It actually, each thread was kind of treated as its own process, so it was actually able to have, you could have one thread running as root and one running as nobody, and have this shared data structure between them, and actually use that to, you could have a completely hardened privileged thread running, and then have one in the nobody context that hasn't had its code audited quite as well, or whatever that causes issues in it, and that can actually cause the other thread to mess up, which in turn can lead to privilege escalation, or privilege escalation of some kind. Although Linux threads isn't even really used anymore, it's been replaced by NPTL, so you're not going to find it in a whole lot of places, but it's still something to keep an eye out for when you're doing pen tests or whatnot. However, Linux capabilities are more common. You do see them in daemons here and there, and they're specifically per thread. So you can actually have you have another instance where one thread can interfere with another thread and cause it to gain capabilities or privileges, even though the other thread was doing everything right. So in conclusion, there's more than one way to accomplish things. You don't always have to resolve or do the out of the box or known method. There's, like I said, I had to cut some time. I had to cut some slides out of this just to be able to get it within reasonably within scope of the time limit. If you guys have any questions, you want to talk about any of this or anything, feel free to find me, or they're in the paper as well. There's at least two more listed in here. One was where you had a structure that ended up with multiple pointers all. You had pointer plus offset, and that pointer pointed to the beginning of the structure, and then you had another pointer in the structure that all ended up pointing to the same place, and you could actually overwrite an integer, which was later used in a loop and caused a stack overflow. The biggest thing to keep in mind is that the heap is persistent and is shared, and because of this, you can actually exploit that condition. Threading provides a really interesting way for taking code that, for instance, under normal circumstances in this code base, I couldn't cause another free to be injected of another chunk in between the two, but threading allowed me to actually accomplish that. And slides are pretty hard to fit code into. I haven't found a good way to do it. Are there any questions? Okay, I guess not.